The standard account of the Cretaceous-Paleogene extinction is one event. An asteroid, roughly 10 to 15 kilometers across, struck the Yucatan Peninsula 66 million years ago and terminated 75% of species on Earth. That account is correct in its primary mechanism, and it has been strengthened by every major study of the last decade. What it leaves out is what the planet was already doing at the same time. On the other side of the world, in what is now Western India, the crust had opened along a system of fissures. Lava was flowing from those fissures in volumes not observed since. It had been flowing with pulses for hundreds of thousands of years before the asteroid arrived, and it would continue for hundreds of thousands of years after. The relationship between these two events is one of the most contested questions in geology. What follows is what the rock record confirms, what remains disputed, and what is now considered unlikely. The Deccan Traps are a large igneous province in west-central India. The preserved lava flows cover approximately 500,000 square kilometers, roughly the area of Spain, and reach thicknesses of more than 2,000 meters in the Western Ghats. The total erupted volume is estimated at about 1 million cubic kilometers. Before erosion and plate tectonic reworking, the original extent may have exceeded 1.5 million square kilometers. The province formed through fissure-fed flood basalt eruptions, driven by the Reunion mantle plume, over a period of roughly 600,000 to 800,000 years, bracketing the KPG boundary at 66 million years ago. Radiometric dating using both uranium-lead and argon-argon methods places the main eruptive interval between approximately 66.3 and 65.5 million years ago. The eruptions did not produce tall stratovolcanoes. They produced basalt floods from kilometer-scale fissures, with individual flows reaching hundreds of kilometers in length and emplacing over thousands of square kilometers at a time. The name comes from the Swedish word trappa, meaning stairs, applied to the stepped terrain that forms when successive horizontal lava flows weather at different rates. Each step in the landscape corresponds to a flow unit or group of units. The total sequence in some sections contains more than 50 individual flows stacked vertically. The lavas are tholeiitic basalts, low in silica, rich in magnesium and iron, with olivine, pyroxene, and plagioclase as the dominant mineral phases. Individual flow thickness ranges from less than a meter to over 85 meters. Some flow units can be traced laterally for hundreds of kilometers before thinning below detectability, which is a standard signature of flood basalt emplacement rather than point source volcanic construction. The cumulative volume is the key metric. A single major eruptive pulse of the Deccan Traps released on the order of 1,000 cubic kilometers of lava and approximately 10 gigatons each of carbon dioxide and sulfur dioxide. For comparison, the 1980 eruption of Mount St. Helens produced about 1 cubic kilometer of ejecta. The Deccan Traps released, pulse by pulse, hundreds to thousands of times that volume of material over an eruptive history spanning several 100,000 years. The underlying driver was the Reunion mantle plume, a column of anomalously hot material rising from deep within the mantle. The Indian plate, moving rapidly northward at the time at over 15 centimeters per year, passed over the plume head around 66 million years ago. The interaction between the thinning lithosphere and the plume produced the initial melt volumes. The province is aligned with the subsequent volcanic track of the Reunion hotspot, which extends southwest through the Mascarene Islands to the present-day location of Reunion in the Indian Ocean. Individual fissures that fed the Deccan eruptions were kilometer-scale linear features, not cone-shaped vents. Modern analogs for this style of eruption are limited. The 1783 Laki fissure eruption in Iceland produced approximately 14 cubic kilometers of lava over 8 months and caused documented climate effects in the northern hemisphere. A Deccan-scale pulse would have released roughly 70 times that volume, sustained over longer periods. No eruption observed in recorded human history provides a close analog for flood basalt emplacement at Deccan scale. The direct physical effect of the lava was limited to the Deccan region itself. Flood basalts are destructive locally. They buried ecosystems in western India under hundreds of meters of molten rock, sterilized the immediate terrain, and altered drainage patterns across the subcontinent. They did not kill dinosaurs in North America. The atmospheric effects are the mechanism that could link Deccan volcanism to global extinction. Basaltic magma carries dissolved volatile gases that release at the surface when confining pressure drops. The major gases are water vapor, carbon dioxide, sulfur dioxide, and smaller quantities of hydrogen chloride and hydrogen fluoride. The volumes released by Deccan-scale eruptions are large enough to modify global atmospheric chemistry for years to centuries after each pulse. Sulfur dioxide is the short-term climate driver. Once injected into the stratosphere, SO2 reacts with water and oxygen to form sulfate aerosols, which reflect incoming solar radiation back to space. Individual historical eruptions, such as Pinatubo in 1991, demonstrate the mechanism. Pinatubo produced global cooling of about 0.5 degrees Celsius for 2 years after injecting roughly 20 megatons of SO2 into the stratosphere. Deccan pulses released thousands of times that amount. Carbon dioxide is the long-term driver. Unlike sulfate aerosols, CO2 does not fall out of the atmosphere on a timescale of years. It persists for thousands of years, trapping outgoing long-wave radiation and warming the surface. A volcanic province that releases sulfur and carbon dioxide together produces a characteristic climate sequence: short-term cooling from sulfate aerosols, followed by longer-term warming from CO2, potentially with rapid transitions between the two as eruptive intensity varies. Ocean chemistry is affected through CO2 dissolution. Carbon dioxide dissolved in seawater forms carbonic acid, which dissociates into bicarbonate and hydrogen ions. The hydrogen ions lower the pH. Acidified seawater is undersaturated with respect to calcium carbonate, which means calcifying organisms, including planktonic foraminifera, coccolithophores, mollusks, and corals, cannot maintain their shells or skeletons at the same rate of secretion. Sulfate deposition from the atmosphere produces acid rain. Sulfuric acid droplets formed in the stratosphere eventually fall out, either directly or as sulfate-enriched precipitation. Terrestrial effects include leaf damage to plants, mobilization of aluminum and heavy metals from soils, and acidification of surface waters. Freshwater lake systems are particularly vulnerable because they have less carbonate buffering capacity than seawater. The 1783 Laki eruption in Iceland, at a scale orders of magnitude smaller than Deccan pulses, produced acid haze and vegetation damage across Europe. Hydrogen chloride and hydrogen fluoride released alongside sulfur dioxide add additional toxicity pathways. Fluorine in particular accumulates in vegetation and surface water. At elevated concentrations, ingested fluorine causes osteofluorosis in vertebrates, a condition that weakens bones and can be lethal over sustained exposure. Fluorine toxicity has been documented in livestock after historical Icelandic eruptions and is a known mechanism of volcanic-caused mortality. These mechanisms are not in dispute. The question is whether the Deccan eruptions produced enough volatile output at the right time to destabilize ecosystems globally in the lead-up to the KPG boundary. The evidence for Deccan-driven environmental change in the late Maastrichtian comes from multiple independent records. Marine osmium isotope records from deep-sea sediments show two major shifts at 66.49 and 66.28 million years ago. These shifts are interpreted as inputs of basalt-derived osmium into seawater, coinciding with known phases of Deccan eruption. They provide a direct chronological link between volcanism and seawater chemistry. Benthic foraminifera, carbon, and oxygen isotope records from the same sediment cores show disruptions of the global carbon cycle and temperature shifts during the final several 100,000 years of the Cretaceous. A warming event known as the Late Maastrichtian warming event is recorded in multiple sections and corresponds broadly to the early phase of Deccan volcanism. Mercury concentrations and mercury isotope compositions in late Maastrichtian sediments from both marine and terrestrial settings show anomalies consistent with large-volume basaltic volcanism. Mercury is released in significant quantities by basaltic eruptions and is a standard proxy for large igneous province activity in the geological record. A 2024 study of glycerol dialkyl, glycerol tetrether compounds in fossilized peat quantified the temperature effect of Deccan volcanism on a terrestrial site. The study found approximately 3 degrees Celsius of warming over the final 100,000 years of the Maastrichtian, attributed to CO2 outgassing, along with a cooling event of about 5 degrees Celsius lasting less than 10,000 years, around 30,000 years before the KPG boundary. This cooling corresponds to the peak of the Paladpur eruptive phase and is attributed to volcanogenic sulfate aerosols. The same study found that by the time of the KPG boundary, global temperatures had returned to pre-event levels. This result is significant. It indicates that the climate disturbance produced by the largest known Deccan pulse before the extinction had dissipated by the moment the asteroid struck. The cooling was short, sharp, and recovered. The central question is the relative timing and magnitude of Deccan eruptions compared to the Chicxulub impact. Two high-precision geochronology studies published in 2019 reached different conclusions on this. Schoen and colleagues, using uranium-lead dating of zircons, found that the main eruptive pulses occurred in 4 intervals of roughly 100,000 years each, with significant activity straddling the KPG boundary. Sprain and colleagues, using argon-argon dating, concluded that more than 75% of the total lava volume erupted within approximately 600,000 years after the boundary. On the Sprain chronology, most of the Deccan Traps erupted after the dinosaurs were already extinct. The two studies used different samples and different methods. Both were published in the same issue of Science. The disagreement has not been resolved. An older hypothesis, proposed by Rennie and colleagues in 2015, suggests that the Chicxulub impact itself triggered intensification of Deccan volcanism by destabilizing the magmatic plumbing system through seismic energy transfer. This would make the largest Deccan pulses a consequence of the impact rather than an independent cause of extinction. The hypothesis remains debated and is not accepted as established. The fossil record adds constraints. Dinosaur diversity in the late Maastrichtian is the subject of a long-running debate. Some studies report declining diversity in the last several 100,000 years of the Cretaceous, consistent with Deccan-related environmental stress. Other studies using sampling-corrected methods and broader geographical coverage find no significant decline and interpret the extinction as abrupt, driven by the impact with minimal prior stressor contribution. The core difficulty is sampling bias. The fossil record for the final million years of the Cretaceous is concentrated in a small number of well-studied formations, particularly the Hell Creek Formation of Montana, North Dakota, South Dakota, and Wyoming. Inferences about global dinosaur diversity drawn from North American sections may not represent the worldwide pattern. Attempts to correct for this using statistical subsampling have produced different conclusions depending on the method applied. The question of whether dinosaurs were in decline before the impact is methodologically difficult and remains open. Marine invertebrate records are more complete because calcareous microfossils accumulate in deep-sea sediments at higher temporal resolution than terrestrial vertebrate fossils. Planktonic foraminifera assemblages across the KPG boundary show a sharp synchronous collapse at the boundary itself, followed by a slow recovery interval. The pre-boundary interval shows assemblage changes interpreted variously as Deccan-driven stress or as normal Cretaceous turnover. The ammonites, a dominant Mesozoic cephalopod group, had been declining through much of the late Cretaceous for reasons unrelated to either the Deccan or Chicxulub, and their final extinction occurs at the boundary. A 2023 Dartmouth study using machine learning models to invert the fossil record concluded that Deccan volcanism alone could have produced extinction-scale effects, even in the absence of an impact. A 2022 study in southeastern China found mercury anomalies coinciding with what the authors described as a gradual dinosaur decline in that region. Neither result is a consensus finding. The current scientific consensus, as reflected in the 2024 literature and standard reference works, is that the Chicxulub impact was the primary cause of the KPG mass extinction. Deccan volcanism is recognized as a contemporaneous large-scale event with documented environmental effects, but its contribution to the extinction itself is treated as secondary or uncertain. The 2024 GDGT result showing temperature recovery before the boundary has weighed against the strong Deccan hypothesis. The Chicxulub impact produced effects that the Deccan Traps on current evidence could not match. The impactor was approximately 10 to 15 kilometers in diameter. It struck the Yucatan carbonate platform at high velocity and excavated a crater roughly 180 kilometers across the Chicxulub structure. The target rock was rich in anhydrite, a calcium sulfate mineral. Impact-induced vaporization injected sulfate directly into the stratosphere, producing an impact winter estimated at months to years of suppressed sunlight and global cooling. Ejecta from the impact includes the global KPG boundary clay layer found on every continent. The layer contains an iridium anomaly consistent with asteroidal material, shocked quartz with planar deformation, features consistent with shock pressures, above 10 gigapascals, and microtektites and spherules interpreted as solidified droplets of impact melt. This assemblage is the strongest global scale impact signature in the geological record. The iridium signal itself is distinctive. Iridium is rare in Earth's crust, but present at elevated levels in certain asteroid types, particularly carbonaceous chondrites. The Alvarez team's 1980 identification of an iridium spike at the KPG boundary in Italian sections at Gubbio provided the original impact hypothesis. Subsequent sampling found the same iridium anomaly at boundary sections on every continent, at concentrations up to several hundred times background levels in the thin clay layer itself. The kill mechanism was acute. Direct thermal radiation from atmospheric re-entry of ejecta ignited wildfires across continental scales. The re-entering ejecta heated the upper atmosphere for hours after the impact to temperatures that could ignite dry vegetation below. Soot from those fires, combined with impact sulfates and fine dust, produced a sunlight-blocking atmosphere that suppressed photosynthesis for approximately 6 months to 2 years, depending on the model. Marine food webs anchored by calcareous plankton collapsed. Terrestrial food webs anchored by primary productivity collapsed. Global cooling estimates for the impact winter range from about 10 to 25 degrees Celsius of surface temperature drop, sustained for months. This magnitude of cooling, applied globally over a short interval, is sufficient to collapse most ecosystems independent of any other stressor. The combination of darkness, cold, and acid rain from the sulfate aerosols constituted a multi-mechanism kill event. The iridium anomaly, the shocked quartz, the microtektites, and the geographical distribution of the ejecta layer are not explained by any other proposed mechanism. A volcanic province does not produce shocked quartz of the Chicxulub variety, does not produce the iridium abundance observed at the boundary, and does not deposit a globally synchronous ejecta layer of the observed composition. Dinosaur fossils are found up to the KPG boundary layer. They are not found above it. The extinction, at least at the boundary itself, is abrupt in the terrestrial record to the resolution that the record permits. The question that remains is whether Deccan volcanism changed the outcome. One version of the argument holds that the pre-impact phases of Deccan eruption weakened ecosystems by introducing climate variability and ocean acidification, so that when the impact arrived, the biosphere was already destabilized and less able to absorb the shock. On this view, without Deccan stress, the impact might have produced a severe but recoverable event rather than the full KPG extinction. A second version of the argument holds that Deccan eruptions played a role in delaying post-extinction recovery, rather than in the extinction itself. Marine foraminifera took approximately 300,000 years to recover full diversity after the KPG boundary. Some of the later Deccan pulses fall within this window. Continued volatile input may have suppressed ecosystem reconstruction. A third version, consistent with the 2024 GDGT result, holds that Deccan eruptions produced measurable but transient climate effects, that temperatures had returned to baseline by the time of the impact, and that the extinction is explained by the impact alone without requiring a volcanic co-driver. All three positions are defended in the current literature. The primary reason the question has not been settled is that the relevant dating uncertainties are larger than the time windows being compared. Determining whether 75% of Deccan lava erupted before or after the boundary requires precision at the scale of tens of thousands of years across a 66 million year distance. The high-precision techniques available have narrowed the uncertainty, but have not eliminated it. What is agreed is the sequence of events. Large igneous province activity began at some point in the late Maastrichtian. The climate showed measurable disturbance during the final several 100,000 years. A 10 to 15 kilometer asteroid struck the Yucatan 66 million years ago. A global mass extinction event occurred at the same stratigraphic boundary. Volcanic activity continued for several 100,000 years afterward. Biodiversity recovery to pre-extinction levels required roughly 10 million years. The Deccan Traps remain the most accessible flood basalt province on Earth. The stepped landscape is visible across much of Maharashtra, Madhya Pradesh, and Gujarat. The Western Ghats escarpment exposes sections over 2,000 meters thick. Some of the temples of the Ajanta and Ellora complexes are carved directly into the basalt. The province is one of several known continental flood basalts. The Siberian traps, erupted at the end of the Permian 252 million years ago, are associated with the largest extinction event in Earth's history, in which approximately 96% of marine species disappeared. The Siberian eruptions produced an estimated 4 million cubic kilometers of basalt and intruded through evaporate and coal-bearing sediments, generating additional volatile release through thermal decomposition of the sedimentary target rock. The Central Atlantic magmatic province, erupted at the end of the Triassic 201 million years ago, is associated with that period's extinction. The correlation between large igneous province eruption and mass extinction is robust across the Phanerozoic, though the strength of the causal link varies between events. Volume alone does not determine the extinction effect. The target stratigraphy through which the magma erupts matters because it determines the volatile load released with the lava. Siberian magmas intruding coal and evaporate deposits released far more sulfur, chlorine, and organic volatiles per unit magma volume than Deccan magmas intruding primarily crystalline Precambrian basement rock. This is one reason the end Permian extinction was more severe than other flood basalt-associated events, despite the Deccan and Camp events having comparable total erupted volumes. The Deccan case is distinctive because it is the only flood basalt province that overlaps in time with a well-documented extraterrestrial impact of extinction-level magnitude. This coincidence is what makes the event geologically significant and scientifically contested. Without Chicxulub, the Deccan Traps would be straightforwardly implicated in the KPG extinction by analogy to other flood basalt provinces. Without the Deccan Traps, Chicxulub would be straightforwardly implicated by its magnitude and its ejecta record. Both events occurred. The attribution problem is a result of the coincidence. The Réunion hotspot, which produced the Deccan Traps, is still active. It lies beneath the island of Réunion in the Indian Ocean, approximately 3,500 kilometers southwest of the original Deccan eruption sites. The volume of activity at the hotspot today is orders of magnitude below the KPG pulse and represents the tail end of a long-lived plume system. The extinction of the non-avian dinosaurs 66 million years ago is documented by a clear stratigraphic signature, a global ejecta layer, and the fossil record. The Chicxulub impact is established as the trigger at or immediately before the boundary itself. The Deccan Traps are established as a contemporaneous flood basalt event that released large volumes of CO2 and sulfur dioxide and altered the climate for periods of tens of thousands of years during the late Maastrichtian. The extent to which those volcanic effects contributed to the extinction remains a question the current evidence does not fully answer. What the rock record permits, stating clearly, is that both events occurred. An asteroid 10 to 15 kilometers across struck the Yucatan, and a continental-scale flood basalt province erupted in India during the same geological interval. The dinosaurs, the mosasaurs, the ammonites, and the large calcareous plankton did not survive the combined interval. The mammals, the birds that descended from theropod dinosaurs, and a fraction of marine and terrestrial lineages did. The recovery interval gives one additional data point. Biodiversity took approximately 10 million years to return to pre-extinction levels. Marine foraminifera diversity recovered more slowly than terrestrial vertebrate diversity, which took perhaps several million years to stabilize. The shape of the recovery curve is consistent with removal of most productivity at the base of the food webs and the subsequent reconstruction of ecosystem complexity from small surviving lineages. The Deccan Traps are still visible. The Chicxulub crater is buried under Paleogene carbonates, but has been drilled and imaged. Both events are preserved in the geological record in ways that allow them to be studied directly. The question of how they combined is open. The evidence for each independently is not.